She'd change it all if her hair was still red. The folks that set our lives together should. Okay, we're live. Okay, so chapter 8, continuing from where we left off, we are looking at. Oopsie. What are we looking at? We are looking at problem 58 or 62. Did I do 58 already? I think I did. That's the one where I was tired, and yes, that's the one where I needed to do that. Okay, so problem 62. Used in welding metals, the reaction of acetylene with oxygen has an enthalpy change of negative 1,256.2 kilojoules. How much PV work is done in kilojoules, and what is the value of delta E in kilojoules for the reaction of 6.50 grams of acetylene at atmospheric pressure if the volume change is negative 2.80 liters? Okay, so to do this one, what we're looking at, once again, where's the thing? We're doing this. Bringing this up. Okay. So, delta E equals Q plus W equals. So Q is going to be our delta H. Yep. So 6.50 grams of acetylene. So 6.50 grams times grams per mole. So acetylene is going to be about 24 plus 2 is about 26. 24.022 plus, there we go. 26.038 grams per mole. All right, so that gets us our moles of acetylene times negative 1,256.2 kilojoules per. And the balanced reaction just has the 1 mole of acetylene per 1 mole of acetylene. So that makes that simple. And that gives us our Q. 6.5 divided by 26.038. 38 times 1256.2 is negative 313 point, well, call it 59 kilojoules. Okay, so that gives us our Q. Now W is PV, so it is atmospheric pressure. So 1 atmosphere and the volume change is negative 2.80 liters. So W equals P delta V. So 1 atmosphere, negative 2.80 liters, 101.325 joules per liter atmosphere. Okay. So 1 times 2.8 times 101.32. 101.325. Man, this keypad sucks. It is negative 283.71 joules. So Q plus W is going to be that plus 313.59. Delta E is equal to negative 597.3 joules. Assuming... Oh, no. Work is... Ooh, oofa-doofa. Boom. Okay, so it's definitely not that. So work is a positive value, so it's going to be 283.71 minus 313.59. Delta E is actually negative 29.88 joules. Whew, that was close. I think I'm going to need to shut the door of my room because the cat and the dog are awful playful tonight. So 62, negative 314 kilojoules. Okay, because this is joules, and that's kilojoules. Okay, so I wasn't paying attention. I was not paying attention. So 0.28371 minus 313.59. So it changes a little bit. It changes it just a little bit. Joules and kilojoules. Pay attention to your units, Johnny. All right. What page was that? 313? Close. Okay, and what problem is next? 64, then 66, then 68. So, the familiar ether used as an anesthetic agent is diethyl ether, C4H10O. Its heat of vaporization is positive 26.5 kilojoules per mole at its boiling point. How much energy in kilojoules is required to convert 100 milliliters of diethyl ether at its boiling point from liquid to vapor if its density is 0.7138 grams per mil? All right. So, 100 milliliters times 0.7138 grams per milliliter times grams per mole. We need the molar mass of our diethyl ether. So it's C4H10O, so 12.011 times 4, 1.008 times 10, and 15.999. 74.123 grams per mole gives us our moles of diethyl ether. And then we multiply by 26.5 kilojoules per mole. Yep, that's all it's going to take. So 100 times 0.7138 divided by 74.123 times 26.5, 25.5 kilojoules. Yep. Huzzah! Okay. Okay, so I'm definitely awake this time. I'm doing all right. So, now, next up is problem 66. Aluminum metal reacts with chlorine with a spectacular display of sparks. How much heat in kilojoules is released on reaction of 5 grams of aluminum? All right. So we have our balanced reaction. We have 5 grams of aluminum. So 5.00 grams of aluminum. Let's see, it's 26.0, no, 26.1, 26.982. 26.982 grams per mole of aluminum times, let's see, what is it? It's negative 1,408.4 kilojoules per 2 moles of aluminum. So, like I warned in class, the balanced reaction gives you the number of moles that go on bottom. Oh, pup, stay off the mic stand. All right, so 5 divided by 26.982 times 1408.4 divided by 2 means that it is going to be negative 130.5 kilojoules. Technically, there's only 3 sig figs, but the book doesn't seem to care very much about that. But I'm still going to double check. 66, 131, yeah. Okay. Okay. 68. How much heat in kilojoules is evolved or absorbed in the reaction of 2.5 grams of iron 3 oxide with enough carbon monoxide produced iron metal? Is the process exothermic or endothermic? Well, first off, it's a slightly exothermic process. Iron 3 oxide plus 3 carbon monoxide. So, 2.50 grams of Fe2O3 times 55.845 times 2 plus 15.999 times 3. Okay, so 159.687 grams per mole of Fe2O3, and it releases a very small amount of energy, negative 24.8 kilojoules per 1 mole of Fe2O3. So a balanced chemical reaction, the coefficient in front of iron 3 oxide is 1. So simplifies things. 2.5 divided by 159.687 times negative 24.8 is negative 0.388 kilojoules, or negative 388 joules. Okay, dog. He's a sweet boy. Okay, so after 68, who comes next? 74, 76, 78, 80, 82. Okay, so we're going to do 74 through 82. What phase of matter is associated with the standard states of the following elements in compound? Chlorine is a gas at room temperature, mercury is a liquid, carbon dioxide is a gas, and gallium is probably a solid. But I know it has a very low melting point, but I think it's a solid. Yeah, it looks to be a solid. Let's see. Yes, it is a solid. Yeah. Okay. 76. Write balanced equations for the formations of the following elements, compounds from their elements. Okay, so remember, formation reactions, you always produce 1 mole of your product, which means you're going to have fractions for everything else. So iron 3 oxide means Fe2O3, so iron plus oxygen, solid iron, gaseous oxygen, goes to form solid Fe2O3. So we need 2 of these and 3 halves oxygen. Sucrose. We're making, okay, and we need hydrogen gas and oxygen gas. C12H22O11, solid. So we're going to need 12 carbons. We're going to need 11 molecules of hydrogen and 11 halves oxygen. Uranium hexafluoride. So we're combining uranium, a solid, plus fluorine gas, a gas, to make UF6 solid. So 3 of those. Okay. So formation reactions aren't particularly challenging. 78. Sulfuric acid, the most widely produced chemical in the world, is made by a 2-step oxidation of sulfur to sulfur trioxide, followed by reaction with water. Calculate the delta H formation for sulfur trioxide in kilojoules per mole, given the following data. All right, so our 2 reactions that they've given us are sulfur plus oxygen makes sulfur dioxide, and then the sulfur dioxide plus 1/2 oxygen makes sulfur trioxide. So what we're trying to get is sulfur plus 3/2 oxygen makes sulfur trioxide. So all we need to do is just add these 2 reactions together. The sulfur dioxide cancels out, and you're left with S plus 3... Oh, okay. 3/2 oxygen makes SO3. So we're just adding these two reactions. So we're just going to need to add those two values. So 296.8 and 98.9, both negative. So we add those together. I'm going to get 7, 5, 9, 3, negative 395.7. So that is a very simple, very straightforward Hess's law problem. 80. The standard enthalpy change for the reaction of sulfur trioxide with water to yield sulfuric acid is delta H standard is equal to negative 227.8. Use the information in problem 8.78 to calculate the delta H of formation for H2SO4 in kilojoules per mole. For liquid water, the enthalpy of formation is negative 285.8. So, we're trying to find H2 plus S plus O2 yields H2SO4. Yep. Given S plus O2 yields SO2, SO2 plus 1/2 O2 yields SO3, and H2 plus 1/2 O2 yields H2O. Okay, do I have an... Oh, and also H2O plus SO3 yields H2SO4. So I have all of these numbers. So let's see, negative 296.8, negative 98.9. Delta H of formation for liquid water is negative 285.8. And for H2O plus SO3, makes H2SO4, is negative 227.8. So, in fact, I think I can just add these together as they are, because SO2 cancels out, SO3 cancels out, water cancels out. We're going to have H2 plus S plus 2 oxygens. Yep, so I just need to add these four numbers together. Once again, the simplest of Hess's of laws. So 296.8 plus 98.9 plus 285.8 plus 227.8. The enthalpy of formation is negative 909.3. Okay. So they were a little bit tricky about that one, but not excessively so. Okay, now 82. Styrene, C8H8, the precursor of polystyrene, has a standard heat of combustion of negative 4,395 kilojoules per mole. Write a balanced equation for the combustion reaction and calculate the enthalpy of formation for styrene in kilojoules per mole. Okay, so enthalpy of combustion just means you burn 1 mole of the thing. So C8H8 plus O2 yields 8 CO2 plus 4 H2O. 4 plus 16 is 20, so we need 10 oxygens. All right. So that is the enthalpy of combustion for styrene, negative 4,043.95. So that means when we flip it around, I'm going to need a new sheet of paper. So when we flip it around, it's going to be 8 CO2 plus 4 H2O yields C8H8 plus 10 O2, positive 43.95. The reason I need to flip it around is because we are trying to find the enthalpy of formation for styrene. And so the regular formula, so C, graphite, plus H2 yields C8H8 So let's see, to make CO2, we're doing C plus O2 yields CO2. Enthalpy of formation for that is negative 393.5, but we're going to need to multiply this boy by 8, because 8, 8, 8, 8 and 4, because we're canceling out the CO2. And then we're going to do 4H2 plus, let's see, 2O2 yields 4H2O to cancel out the water. So it's going to be negative 285.8 times 4. And yep, that cancels out all the oxygen, that cancels out the CO2 and the H2O. We're left with 8 carbon and 4 hydrogen makes C8H8. So we just add those together. So move it up so you can see it all. 4395 minus 393.5 times 8 minus 285.8 times 4 is positive 103.8 kilojoules per mole. Okay, I believe that was the end of that particular streak. Yep, so now 86, 88, 90, 92, 94, 96. So now we're going to be doing 86 through 92. Given the standard heats of formation shown in Appendix B, what is the change in enthalpy in kilojoules for the reaction calcium carbonate when calcium oxide plus CO2? It is positive 294, I think, but we're going to have to go to the appendix to check. So let's see, the appendix starts A10. All right, so calcium. Okay, so we're doing calcium carbonate goes to calcium oxide plus CO2. It's all 1 to 1 to 1, so the enthalpy of reaction is products minus reactants. Calcium oxide is negative 634.9. CO2 is negative 393.5. And calcium carbonate is negative 1207.6. 1207.6 minus 634.9 minus 393.5. 179.2. I misremembered. Could have sworn it was 234. Okay. Yeah. So that the enthalpy of formation problems are, I think, fairly straightforward. 88. Use the bond dissociation energies on page 296 to calculate an approximate delta H in kilojoules for the reaction of ethylene with hydrogen to yield ethane. Okay, so bond dissociation energies. Oh, crap, but what you gonna do? So okay, so like I said in class, I really recommend that you draw out Lewis structures for these because ethylene or ethene looks like that, and then we have a hydrogen molecule, and then we're going to see ethane. Okay, so we have a carbon-carbon double bond, we have 4 carbon-hydrogen single bonds, and we have a hydrogen-hydrogen single bond. And then over here we have a carbon-carbon single bond and 6 carbon-hydrogen single bonds. So now we bop on back to page 296. So, carbon-carbon double bond, 728. Carbon-hydrogen single bond, 410. Hydrogen-hydrogen single bond, 436. Carbon-carbon single bond, 350. So we add up all of our reactants, we add up all of our products, then it's going to be reactants minus products. So 728 plus 410 times 4 plus 436. It's 2804. 350 plus 410 times 6. 2810. Reactants minus products is -6 kilojoules per mole. So that is a pretty small number. So let's and 88 is, yep, -6. That is kind of ridiculous. Okay, so now, all right, now 90. Calculate an approximate heat of combustion for butane in kilojoules by using the bond dissociation energies. Okay. All right, so we are, okay, so butane, C4H10. So we're going to have 3 carbon-carbon bonds, and we're going to have 10 carbon-hydrogen bonds. Oh, we need to balance it. Let's see, so C4H10 plus O2 yields CO2 plus H2O. We're going to need 4 of these and 5 of these, so we're going to need to double this. That's going to be 8, 10, 16 plus 10 is 26, so 13 oxygens. So we're actually going to have 6 carbon-carbons and 20 carbon-hydrogens, as well as 13 oxygen-oxygens. And on the other side, we're going to have 16 carbon-oxygens and 20 hydrogen-oxygens. So this is 498, this was 350, this is 436. They tell us here that carbon dioxide is 804. And for hydrogen oxygen, I can't remember, but I think that's 350 to 96. Oh, nope, 460. So we add up all of our reactants. So 6 times 350 plus 20 times 436 plus 13 times 498 is 17,294. 16 times 804 plus 20 times 460 is 22,064. That minus that is equal to 17,294 minus 22,064, negative 4770. What does entropy measure? Measures the transfer of heat at a certain temperature. It measures randomness. It measures disorder. It measures freedom. Freedom's just another word for nothing left to lose. So let's see what they say. Entropy is a measure of molecular randomness. All right, 90. I think it was 94, 96, yeah. Oops. How is it possible for a reaction to be non-spontaneous, yet exothermic? Nope, that's 95. How is it possible for a reaction to be spontaneous, yet endothermic? Yeah, endothermic reactions do tend toward non-spontaneity. However, if there is an increase in entropy, then it can be spontaneous, particularly at high temperatures. 96. Tell whether the entropy changes for the following processes are likely to be positive or negative. The fizzing of a newly opened can of soda. That is going to be positive because you have the dissolved carbon dioxide coming out of solution and entering the gas phase. And thus it is more free to explore because now it's a gas. The growth of a plant from a seed, that is negative. Life in and of itself is a decrease in entropy. There is a corresponding increase in entropy for the universe at large once life, releases energy as heat. But all right, next is 100, I believe. 100, 102, 104, 106. Okay, we're in the end game here. One of the steps in the cracking of petroleum into gasoline involves the thermal breakdown of large hydrocarbon molecules into smaller ones. For example, the following reaction might occur. C11H24 into C4H10 plus C4H8 plus C3H6. Is the delta S for this reaction likely to be positive or negative? It's going to be positive because you have multiple things being created from one thing. Also, the C11H24 is very likely to be a liquid at room temperature, whereas these guys are mostly gases at room temperature. Let's see what they say. A32. 100. Reaction increases the total number of molecules, so delta S is positive. All right, tell whether the reactions with the following values of delta H and delta S are spontaneous or non-spontaneous, and whether they are exothermic or endothermic. So A, delta H is negative 48, delta S is positive 135, and the temperature is 400 Kelvin. All right, so these are all delta G equals delta H minus T delta S. So A and B are both exothermic, C and D are both endothermic, because of the values of delta H. Now, whether they're spontaneous or not, delta G is equal to positive or negative 48,000 minus 48,000. Oh, and you won't be able to see what I'm writing. Minus 400 times positive or negative 135. So, calculator. So, 48,000 minus 400 times 135 is negative 102,000. So, the first one, A, is spontaneous. Okay? So, that's with a negative delta H and a positive delta S, which means, so A, B, C, D, which means that D, which has the opposite signs, positive delta H and negative delta S, is going to be positive 102,000, and therefore is going to be non-spontaneous. B, delta H and delta S are both negative, so 48,000 minus 400 times 135 is positive 6,000, and therefore non-spontaneous. This one is negative 6,000, and therefore is spontaneous. Okay, so 104, then 106, and we are so close to done. Suppose that a reaction has delta H equals negative 33 and delta S equals negative 58. At what temperature will it change from spontaneous to non-spontaneous? So the equilibrium temperature, TEQ, is delta H over delta S, and that is negative 33,000 divided by negative 58 joules per Kelvin. So it's going to change at 569 Kelvin. Or 570, two sig figs. Anyway, let's see. It's a negative change in entropy, so it's going to be spontaneous at low temperatures, non-spontaneous at high temperatures. And 106. Which of the reactions in problem 102 are spontaneous at all temperatures, which are non-spontaneous at all temperatures, and which have an equilibrium temperature? Okay, so that's basically asking us about this guy. So positive, negative, positive, negative. Okay, so this one's always, this one's never. This one is going to be at high temperatures. This one is going to be at low temperatures. Okay. Okay, so always spontaneous is exothermic with an increase in entropy, and that is A, always spontaneous. Never spontaneous is endothermic with a decrease in entropy, and that is going to be D, never spontaneous. Okay. High temperatures is when they're both positive, so that would be C. Low temperatures is when they're both negative, and that would be B. All right. Meaning that B and C have equilibrium temperatures. A is always spontaneous, and D is never spontaneous. All right, and that is it for Chapter 8. I'll be back in a few minutes to continue new videos on Chapter 9. See you in a few.